for the poster session. So today we have me, then Márcio, Jamile, Maria, and Carlos. And for the next week, João, Vinícius, Jacinto, Yoxara, and Álvaro, okay? Did I miss someone? Please let me know.
All right. Carlos, could you set up the other one there? So just one is more information regarding today's dinner. So we'll be at the Tábua de Carne, is in Ponta Negra. So it's very close to the hotel where you are. So it's not far, it's very close. Okay. So from the hotel for the Pousada O Tempo e o Vento, you can go walking if you want. So, but there will be a bus taking everybody at the Praia Mar Hotel at 7 o'clock and take everybody to the restaurant. The bus will be waiting for us there until we are done eating and drinking back to the Praia Mar Hotel. Clear? One key information is that, so for those who are going to the restaurant and have paid the conference fee, so you don't have to pay for anything else, but besides the food, beer
some time ago to give this talk here, and I was telling him that, well, he suggested me to talk about this topic, and that was very good because this paper was already submitted, and then I received the first comments from the referee, and when I was preparing this talk, I realized that some of the most important aspects of this work were not really emphasized in the paper. So I decided to rewrite the paper after this, preparing this presentation. I'd like to thank Ferdinand for that too. So I'm going to talk about the possibility of measuring dark matter density parameter in a model-independent way. Of course, today in cosmology, you know, we have a lot of alternative cosmologies, and testing them in in a proper way is very important, and then therefore we need model-independent measurements of cosmic quantities, right? To have a fair competition between these alternative models and the Lambda-CDM, the standard cosmology. As I said, this is a paper that was submitted recently, and this is written with some collaborators, Rodrigo Holanda, who is a professor here in this Federal University of Rio Grande do Norte, Rodrigo Gonçalves, who is a postdoc at ON, and Javier Gonçalves, who is right there and is a postdoc here at UFRN too. Okay, so I'm going to talk a little bit about Lambda-CDM and its tensions, discrepancies, crises, and so on. Then I'm going to talk about a model-independent way to estimate omega m, right, using galaxy clusters observations and type 1a supernovae. Then I'm going to test the possibility of departures from the standard dark matter evolution, right? That I'm going to parameterize by this parameter epsilon, right? And perform some forecasts on the epsilon parameter. How can we detect these departures in the future? Then I'm gonna go to my main conclusions. Okay. So this is the standard cosmology summarized in this paragraph. I don't know how many of you are familiar with that, but summarizing this in this paragraph is just this. The universe is spatially flat and accelerating, composed of baryons, dark matter, and dark energy, underwent a hot, dense, early phase of expansion that produced the light elements via Big Bang nucleosynthesis and the CMB radiation, and experienced a much earlier epoch of accelerated expansion known as inflation, which produced density perturbation from quantum fluctuations, leaving an imprint on the CMB and isotropy and leading by gravitational instability to the formation of the large-scale structure that we observe today, right? So this is the standard cosmological model. Of course, it's based and built, it's supported by many observations, right? And of course, there are many aspects in this standard cosmology that we don't know for sure that need to be verified by further observations. Like, for example, the nature of the dark matter. Of course, I think I can't say anything about if dark matter exists or not here in this conference, right? But some people in cosmology work with modified gravity and believe that it may be dark matter may be the manifestation of this modified gravity, right? But the nature of dark energy and so on, if there was an inflationary epoch or something different. So there are many aspects of this model that have to be verified by future observations, okay? But the point is, the Lambda-CDM is a very good description of the universe, right? It fits most of the observational data that we have today, right? Of course, there are some theoretical problems, right? Like, for example, the cosmological constant problem. We don't know why there is this discrepancy between the value of the lambda that comes from quantum field theory and the one that should be observed by cosmological observations. But the fact is that it's an excellent fit for most of the data we have today, right? So here we are showing this plane, omega m and omega dark matter, right? So we have constraints from CMB, supernovae clusters. If I put baryonic acoustic oscillations here, it's going to be like this. So we have a concordance cosmology, right? But recently, we have also, there are many tensions and discrepancies in the context of the Lambda-CDM cosmology reported in the literature, right? I'm going to give a very brief, I'm going to make a very brief comment on this, but there are many, many papers today in the archive today. If you go there, there are for sure there are some people talking about these discrepancies and tension, right? The first of them is in this omega m sigma 8 discrepancy, which is about 2.6 sigmas, right? Standard deviations. That comes from weak length measurements, 2015 and 2017, I think the kids' weak length survey, showing that the sigma 8, which is the normalization of the matter power spectrum, in these for these measurements, are smaller than what's predicted by the the Planck using the Lambda-CDM cosmology as the fiducial model, right? So this is something like 2.6 discrepancy. This is very likely related to to another problem that was verified recently, which is the normalization, the CMB lensing CMB lensing amplitude. That in the Lambda-CDM cosmology is 1, but the Planck data constrain these parameters to be this value, 1.18 plus minus 0.14, right? And this is about 3 sigma away from what is predicted by Lambda-CDM, right? 0.14, right? Sorry, say that again. This is 95% confidence level, right? Okay, 95.4, right? So, so this is again another problem that probably related to this, how the matter is the grounds of perturbation in the Lambda-CDM cosmology. But for sure, the most important of these tensions in the Lambda-CDM model is what now is being called the H-0 crisis, right? Not anymore tension, but a crisis, which is the fact that early data, when the H-0 is estimated using early data, right, in the context of the Lambda-CDM, it predicts a value which is around 67 kilometers per second per megaparsec. But when you go to late-time observations, and some of them model-independent observations, we obtain a value which varies from 4.4 to 6.1 standard deviations of discrepancy, right? So that's the reason why some people call this H-0 tension no longer a tension but a crisis, because we are getting 6 standard deviation of this discrepancy between the Lambda-CDM prediction here and the model-independent measurements here in the local universe. Okay. So in this paper, I think is the last review of this H-0 problem, right? And these authors here, Verdi, Trail, and Adam Riggs, they classified 2 sigmas as curiosity, 3 sigma as a tension, 4 sigma as a discrepancy or problem, and 5 sigma as a crisis. And here we go up to 6 sigma, right? Okay. So it's, okay, so let's see this, yeah. I think that I like to show you something. Okay, this is the power spectrum of CMB. But the point is that the amplitude of the first peak of CMB is directly related to this product, omega m h squared, right? And it's interesting because the Planck data, as I said before, it gives a low value for H-0 and a high value for omega m, 0.32, right? So in some models that try to solve the H-0 problem, right, should predict omega m to be smaller if you want H-0 to be larger, so that you could fit correctly the first peak of CMB, right? But the point is that omega m is usually taking the contents of a model, right? It's different from H-0 that we can use local Cepheids, for instance, and supernovae, and take H-0 without a fiducial model behind, right? But so in this talk, from now on, I'm going to talk about this possibility of measuring omega m, right, in an almost model-independent way, okay? So that we could compare if, in the end of the day, we could have omega m smaller than this, which could be indicated that we have consistency with the Schul's measurements of H-0, which means a larger value of H0, okay? So I hope I'm going to make this clear in the next slides. Okay. So the idea here, a model, almost model independent, I put model independent, not 100% model independent, way to estimate omega m is using the gas mass fraction measurements of galaxy clusters, right? This is the standard expression. The F gas is just the mass of the gas over the total mass of the cluster, right? Which can be put in terms of ρ b, the baryon density, and ρ m, because most of the gas in the cluster, most of the baryons in the clusters are all the baryon content in the cluster, right? So we can do this with some constants here. So there is if you have the measurement of X-ray luminosity, right, from a cluster. So Sasaki, in this paper in 1996, he showed this dependence between the the gas mass fraction X-ray with the distance, the angular distance to the cluster. This is a well-known expression, most of the textbooks in this area of X-ray astronomy. Of course, there are some corrections here, right? For example, this is related to the fact that the baryonic content in the cluster is not exactly the baryonic content in the universe. It's a good representation, but it's not exactly the same. So it's the Planck's factor. This has to do with the mass of the cluster. So it's corrections from weak lengths and so on, right? And we took these two values, which seems to be the most recent values of these two quantities, right? And here, for example, comes from hydrodynamical simulations, which use the Lambda-CDM as a fiducial model. So this is one of the first source of model dependence that I mentioned earlier. Right? Although some authors have tried to estimate this quantity in a model-dependent way and find something very similar. So there is a model dependence, but it's very weak. Okay, this is what I want to say. And these two distances, right? There is a fiducial model that is used in the observations, but this is removed. The dependence of the fiducial model is removed by divided by dA that you want to test if you use this for a cosmological model. And since this has to be a constant as a function of the redshift, the right model is going to be the one that makes F gas a constant as a function of the redshift. Okay? Okay, so I have this expression, and I can invert this equation, right, very easily, and I get this, where now rho m here is rho c, the cold dark matter, and rho b, rho c plus rho b. Okay? So it's a very trivial mathematical step, right? And rho b, of course, goes as a to minus 3 because it's conserved separately, so it's a standard result, right? And of course, here I'm using dl, the luminosity distance, instead of dA, the angular diameter distance. But here, what I did was to use this relation, the duality relation, which is completely model independent, right? This is valid for any geometry, pseudo-Riemannian geometry, so it's completely model independent. So we don't need to care about this. And many people have tried to constrain this equation, this relation, showing that its validity is very well confirmed by observations, right? So in the end of the day, equation 1 furnished a model independent estimate, almost model independent estimate, of the dark matter density pattern, provide that independent measurements of F gas and DL at the same redshift, and we have also rho b 0, right? Okay? So this is the data of F gas that I'm going to use. It's 40 gas mass fraction measurements obtained by Chandra, right? This is the interval of redshift. It was published in 2014 by this group in the United States. Okay, this is the gas mass fraction measurements. And of course, what I need here is DL at the same redshift of the gas mass fraction, okay? I need DL at the same redshift so that I can evaluate this equation, okay? So I'm gonna look for DL measurements at exactly the same redshift of the clusters in the supernovae data, right? And I have this compilation here, which has 1,048 supernovae, right? In this redshift interval. So I proceed in two ways. I need DL at the same redshift of the cluster, and they have 40 clusters, right? So I can do this. I can try to adopt this criterion here, that if the cluster and the supernova are both are more or less the same redshift, the difference between being small than 0.005. So I consider this as a good, more or less at the same redshift, right? They can do this I can look for this data, right, and perform an average here, and I get the points. But I can do better, right? Because doing this, I cannot take into account the systematics, the covariant matrix of the supernovae data, right? So I use a Gaussian process, which is a non-parametric way to reconstruct quantities, right, as a function of a given parameter, and I get very similar results. So I have 40 DLs at the same redshift of the clusters, right, doing these two approaches which are similar, right? So if I have DL at a given Z and the cluster at the same Z, I go back to this equation, to that equation, right, here. I put everything here. Of course, I still need this, okay? But fortunately, there is a very recent 1% measurement of whole B from some absorption systems near a quasar at Z equal 2.52, right, where they measured, they found very low redshift regions where they could measure the deuterium abundance. And deuterium has a clear correlation with the barium abundance, so they can measure the baryonic abundance very precisely with 1% precision, right? This is what they found, right? So here is the deuterium abundance as a function of the oxygen, and this is omega B, H squared, right? So this is the error bars of some previous works, and this is the one that was reporting this publication here, right? And this is the Planck measurements of the same quantity, right? So there is an agreement within 2 sigma between these two measurements of omega B, okay? So, okay, now I have omega B, I have gas mass fraction, and I have DL at the same redshift. So I come back to this equation, put everything there, and let's see what I get. Okay, so this is something different. This is what I get. I get whole C, the energy density of the cold dark matter, as a function of the redshift in almost model independent way, okay? As a function of the redshift. Please do not consider these two codes here. I'm gonna come back later to them, okay? So I have these measurements of whole C, right? Okay? And now I can estimate, finally, omega M and check the results and compare with previous estimate using Lambda-CDM cosmology. And this is what I get if I consider that whole C is proportional to the evolution is the usual 1 plus Z to 3, right? And this is what we obtain, this number, which when I multiply it by the critical density, I get this, 0.13, right, at 1 sigma level. Now, when I compare with the Planck 2018 results, I get something very different. I get something different, right? Because now very different is 6 standard deviation. Now I'll talk about 2.5. But I get 2.4 standard deviations discrepancy, right? Between these model-independent local results and what is predicted by the CMB using the Lambda-CDM model, okay? Okay, if now I use H naught from local cepheids here, right, and supernovae, local supernovae, from the Schulz project, Rees et al. 2019, so I get this, or equivalently omega M, omega total 0.28, right? If you remember, omega M from Planck, in the context of the Lambda-CDM, using the power spectrum, the full power spectrum of the CMB, is 0.31, 32, something like this, right? So this result seems to be that what I am getting here, what I'm obtaining by this, using this approach, is compatible with the Schulz measurements of H0 larger than what Planck predicts, because if you remember, the CMB, the first peak of CMB power spectrum is proportional to the product of these two quantities. There, they predict omega H naught a low value of H naught and high value of omega m. And here is exactly the opposite, right? So this measurement here, not this measurement, this estimate here using galaxy cluster and supernovae seems to be in good agreement with the local values of H naught. If I still want to fit the CMB data as I want to do, right? Okay. Okay, so this is my estimate of omega m, right? 0.28 plus minus 0.013. But note that to perform this analysis, I assumed this, which is completely okay in these kind of models in which the dark matter density evolve conserved separately from the other components, right? Most of the models, including the standard cosmology, predict this, right? But I can go further, right? There are some models in which dark matter and dark energy interact, right? And these necessarily change the evolution of the dark matter, right? As a function of the redshift. So that's the reason why in the beginning I said that I can use this approach to test the evolution of the energy density of the dark matter, right? So, and it's very interesting that in this kind of interacting models of dark matter and dark energy, recently, I think 2 weeks ago, there is this paper in the archive saying that this kind of cosmology is an excellent solution to the H naught and cosmic shear problem, the sigma 8 problem, right? So it seems that this kind of models works very well for the data we have today, right? And because we have to conserve the total energy momentum tensor of the cosmic quantities, so there is an interaction between there are two ways in the standard cosmology. This is 0 and this is 0. The divergence of this is 0, the divergence of this is 0. But in this kind of models, this minus this, the divergence of this sum here is 0, right? So which means that there is a coupling between dark matter and dark energy, okay? Of course, I don't know from first principles how I don't know the form, the mathematical, the functional form of this coupling, right? But of course, I can solve these equations in a very simple way if I suppose that because there is a flow of energy from dark matter to dark energy, or vice versa, so necessarily the energy density of dark matter will evolve differently from the standard case, right? So because it's receiving energy from dark energy, so it's no longer have this kind of H minus 3 scale, right? It's going to be something different from that, okay? Note that if epsilon is larger than 0, then there is a flow of energy from dark energy to dark matter and vice versa, okay? Epsilon in principle may take positive or negative values, okay? Okay, so the point here is to use that approach to test if the dark matter evolution is H minus 3 or not, right? This is what these authors obtained. They obtained a solution for the H naught problem with Xi. This is equivalent to epsilon, right? So it's just, okay. So let's go. Let's see what's gonna happen. So now I am testing this evolution of the dark matter, right? And what I get is something that says nothing, 0.13 plus minus 0.23 at 1 sigma level, right? And what I obtain here is something strange because it's not strange, it's different from the CDM, like in the other case, right? And the discrepancy between the Planck, Lambda-CDM Planck value for omega C and the value that comes from this kind of cosmology is 1.52 sigma different, right? So there is no tension here, right? In the standard case, we saw a clear problem or tension, if you wish. But here there is no tension, right? And this is the values when we put the value of H naught from Schul's measurement. Okay. So again, so first of all, we have a way to test in a model to estimate in a model independent way Rho m, right? But I can also test using this approach the evolution of Rho m if it's a law like this, like in interactive models, or in the standard case, right? And we get completely different results from both approaches. Okay, so what I can do now that I know that I can test the evolution of the dark matter using this data is to do a forecast, because clearly there is no constraint on epsilon from current data, right? And then we performed Monte Carlo, a forecast using Monte Carlo simulation, right? To test, to study the necessary improvements in number and accuracy of upcoming F-gas and supernovae data to detect a non-null interacting parameter epsilon, right? So now we want to know that how many data points we have to have, and which should be the accuracy of this data point in order to detect epsilon different from 0 in the future, using the future observation, right? So we perform a standard Monte Carlo simulation, right? And this is what we get. This is epsilon equal to 0, this red line here, right? And as we expected, if we increase the number of data points, of course, we get more precise measurements on epsilon, right? Here, we use exactly the same features of the data we have today, right? The arrows on the arrows on F-gas, right? And we know we get that if we have 419 points, we would be able to say that epsilon is something different from 0 at 1 sigma level, right? But if we reduce in the simulation the gas mass fraction errors to 50%, so we reduce the number of measurements, the pairs of galaxy clusters and supernovae that we need to check this possibility of epsilon different from 0, right? So it's interesting because this is not an unrealistic number. If you remember that the Rosita, for instance, is expected to detect about 100,000 clusters in the near future, right? So we just did about 300 or 400 to detect interacting using this technique, interacting parameter using this technique, right? So I didn't show you here if I change the supernovae errors, because it does not, these data here do not contribute significantly to any critical, right? So I'm going to get exactly the same number as today, right? So the point is to have more precise measurements of gas mass fraction. This is more important for this analysis. Okay. So I think I have some 2 minutes. So the conclusions of this work is that, of course, Lambda-CDM, we have a standard cosmology that provides a very good description of the data we have today, right? But with only 6 parameters, right? So we are able to describe from the beginning of the universe, from the inflationary phase up to late time cosmic acceleration today, we're using only 6 parameters. So it's a very successful cosmology. But recently we have some discrepancies being reported in the literature. We have discussed about this, sigma 8. I think that today there is this week somebody reported out a curvature tension in the Lambda-CDM model that I'm not going to talk about this today. But the point is, the most important tension was in H0, because we have an observation of H0 here, model completely model independent, and we have a prediction of the Lambda-CDM at high redshift of the same quantity, right? But if we have the same with OM, like I showed here in this talk, so we can compare the Lambda-CDM prediction using early data with the current, with the value that I obtained here using late time data, right? And what we have shown is that there is a kind of tension of 2.4, according to those authors. This is not tension yet, it's just a discrepancy, right? So we have a discrepancy between these two measurements, 2 estimates, and I suspect that it has to do with I suspect that these measurements here is in good agreement with the Schul's value of H naught because of the first peak, the amplitude of the first peak of CMB that we have to fit using the CMB data, right? So we also have, using this approach, a way to test a non-standard evolution of the dark matter, right? And this is what we did. And we performed some simulations to check how many data we have to have in the near future so that we can be able to say if there is a standard or non-standard evolution for the matter density, the dark matter density parameter. Thank you.
Questions?
Question from someone outside the field.